Hey class, Mr. Morris, continuing this crash course in solutions from pre-AP chemistry. We're going to talk a little bit about electrolytes and non-electrolytes. Physical properties of your solutions can be changed, of a solvent can be changed when you add a solute to that solvent. And we want to talk about what that means, what electrolytic behavior is. An electrolyte solution is a solution that conducts electricity. In other words, it will carry an electric current. So you could run a current through it, and it would carry a current just like a wire would carry a current. The solute has to be an ionic compound, an acid, or a base to be an electrolyte. Because in order to conduct electricity, the ions have to move throughout the solution. You have to have ions moving throughout the solution. So then we have strong electrolytes and weak electrolytes. Well, strong electrolytes conduct electricity strongly because they have many ions. Weak electrolytes conduct electricity weakly because they have few ions. Okay. We say that strong electrolytes dissociate or ionize completely, and weak electrolytes, the reason they have few ions is because they do not ionize completely. They do not dissociate completely. We're going to talk more about that later. A non-electrolyte solution is a solution that does not conduct electricity. So we have electrolytes and non-electrolytes. Non-electrolytes don't conduct electricity. If it's an electrolyte, it could either be strong, which means it conducts electricity strongly, or it can conduct it a little bit, conduct it weakly. Right? But a non-electrolyte is something that does not conduct electricity. The typical solute is a covalent compound, like sugar, because it does not break down into ions. So what we want to do is circle, highlight, underline. I'm going to circle because I've got a pen. All of the things that are electrolytes. Watch out for this one. This one's not an electrolyte because the state of matter is solid. Since it is solid, it's not actually an electrolyte. So I think I just underlined it and I wasn't supposed to. Okay, so not this one. That one's not actually an electrolyte, and the reason is because it's solid. It's in the solid state of matter. Remember, an electrolyte is a solution, so we have to find something that's dissolved. Sodium nitrate, this is an ionic compound, so that would be an electrolyte. This one, it's aqueous, but C6H12O6, that's a covalent compound, so that's a non-electrolyte. HCl, that's aqueous. Okay, HCl, that's an acid. Okay, so this is ionic. Then we have an acid. Okay, this is covalent, so it's not an electrolyte. H2O, liquid. That's water, right? It's covalent. That's not going to be an electrolyte. Then I have another aqueous solution here. Sodium chloride. It's ionic. C3H8, that looks like a nonmetal. That's covalent. That's definitely not going to be an electrolyte. And then I have LiOH, that's lithium hydroxide. It's ionic, but it's also a base. It is an electrolyte, so I'm going to circle it. Okay. Then we get into some general solubility rules. Okay. I'll teach you how to read these solubility rules and make some determinations based on it. If something is soluble, if an ionic compound is soluble, it's going to be following one of these rules. Okay, so if it's any of these things are true, then it's soluble, unless there's an exception. All right. In this section down here, the second part of the table, these are insoluble. If you have hydroxide or sulfide, they're insoluble unless it's an exception, one of these. Okay, and then the ninth rule says that anything listed anything that's not listed up here in either of these tables is insoluble. So we've got to be able to interpret those rules. Let's start with the first one, Al2SO4 3. So I'm going to start with the top and look if I look for any reason that I think this might be soluble. Okay, first, is it an alkali metal? Well, if I look at the periodic table, I'd find that aluminum is our metal, and it is not an alkali metal. It's not in group 1. Okay, so I can skip that. Is it NH4? No, this is not NH4. Okay, do we see any of these 3 polyatomic ions? I don't see that. Do you see any of these 4 polyatomic ions? No. Any of these 3? No. I see SO4 though. I do have SO4 sulfate. So then I need to check, is it an exception? If it's an exception, that makes it insoluble in this part of the table. So let's see. Aluminum sulfate, is that combined with lead or mercury or strontium or barium? No, it's aluminum. Aluminum's not any of those exceptions. So that means that this one is what it says in this column. It's soluble. There's a starter. Okay. All right, barium sulfate. Okay, back down. I don't see barium's in group 2, so it's not rule 1. Not any of these. Oh, I see sulfate though. Barium sulfate. SO4 is soluble except when combined with lead, mercury, strontium, or barium. Oh, there's my exception. Barium. So this is insoluble. Insoluble. All right, and then we have copper hydroxide, copper 1 hydroxide, CuOH. So let's see, it's not an alkali metal. I see hydroxide. Okay. It looks like it's probably going to be insoluble, unless, is it a group 1A? No. Is it NH4? No. Calcium? No. Strontium? Barium? No. Okay, copper 1 hydroxide is therefore, it's a hydroxide that's insoluble. By the way, our exceptions down here would make it the opposite, insoluble. So it'd be soluble if it was over in the exception column. All right, potassium hydroxide. So I've got hydroxide. Go over here. When combined with group 1A cations, well, potassium's in group 1A. Oh, I could have known that from up here. So because of rules 1 and 7, I know that this one is soluble, because 1A cations are an exception that make it soluble. And then I get magnesium phosphate, Mg3PO4 It's not group 1A, it's not ammonium, and then I have phosphate. Do I see phosphate here? No. Okay, is phosphate down here? No. I didn't see phosphate, and I also don't see magnesium as any of these rules. Oh, anything not listed above is considered insoluble, so I could put insoluble. All right, I want you to make sure that you understand the state of matter also. If I say something's soluble, that means once I put it in water and I start stirring it up, it's going to dissolve. So if it's soluble, that means that if I put it in water, our state of matter would be aqueous. Insoluble, my state of matter is going to be solid because it doesn't dissolve, so it's still a solid. All right, copper hydroxide, it's insoluble, so I'm going to put solid. This one's soluble, I'm going to put aqueous. And this one's insoluble, so I'll put solid. Okay. Now there's something else it tells us to do. It says to determine whether each compound is soluble or insoluble. If it is soluble, write the dissociation reaction. Well, I want to show you how to do that. A dissociation reaction is showing us how that the ion is going to break apart, the ionic compound is going to break apart in aqueous solution. So what you look at is the first name and the last name. You look at your two different ions that you have. So in this ionic compound, aluminum sulfate, I've got aluminum ions and I've got sulfate ions. So my dissociation reaction is going to look something like this. Al2, SO4, 3. When it dissolves, it's going to break apart into how many aluminum? Well, it's going to be 2 aluminum. And I need to know the charge of aluminum. If you look at your periodic table, it's got that nice little staircase going upward from silver to zinc to aluminum. That's my way of remembering aluminum's at the top of the staircase. It's the third one, so it's got a positive 3 charge. Okay, so I have 2 aluminum ions with positive 3 charge. I have 3 plus 3 sulfates, SO4, with a negative 2 charge. And by the way, if it's soluble, dissolved in aqueous solution, that means it's going to break apart into its ions. So it's going to split in half, and we're going to have 2 of those ions and 3 of these ions. But it doesn't break apart. The polyatomic ions don't break apart any farther. They stay together. All right, insoluble, insoluble. Let's look at KOH. Well, I've got potassium hydroxide. OH is its own thing. All right, so I have KOH yields K with positive 1 charge plus OH with a negative 1 charge. That is how you write a dissociation reaction. This is key to understanding the next topic, which is net ionic equations. I'm going to pause the video here and we'll wrap it up with that.